So for today, our essential question is, what is a derivative and how do I apply this concept of a derivative to rates of change? What makes a function differentiable? So let's build on our concept of rates of change from pre-cal. We know that a rate of change plays into the relationship between two changing quantities. An example that we tend to be familiar with is that of velocity, where velocity is the rate of change of position with respect to time. And we can find an average velocity along an interval, let's say from t1 to t2, by finding our change in the position and dividing it over the change in time. In general, symbolically, we can call this delta S if S is our position function, over delta T, the change in time. And if we had a function to plug into, we would plug T2 into our S function, plug T1 into our S function, and divide by our change in time. So this is just slope, y2 minus y1 over x2 minus x1. Now, a simple example, let's say I travel 200 miles in 4 hours, then my average velocity over this 4-hour period is change in time of 200, change in position of 200, change in time of 4 for an average of 50 miles an hour. Now, does that mean that I went 50 the entire time? No. Could I have been going faster at any moment or slower at any moment? Absolutely. I could also consider something called instantaneous velocity. And so that would be your velocity at an instant. Now, instantaneous velocity is trickier to compute because we would have to divide by the length of time. And if it's at an instant, then that length of time is 0. But while we may not be able to calculate it, we can actually estimate the instantaneous velocity by computing our average velocity over successively smaller intervals, and then finding the limit of the average velocity as we get closer and closer to 0 with respect to our time intervals. So let's make this make a little bit of sense. Let's say I have a position graph over here to the right, and let's call this time number 1, and let's call this time number 2, and this is the graph of my S of t function. So right here, this would be S of time number 1 and S of time number 2. Now, if I look at this graph and I connect a secant line between these 2 points and find the slope of that secant line, and actually let's connect it, that would be my average rate of change. So my secant line drawn through T1 S of T1 and T2 S of T2 would be my average rate of change. But that slope is not going to be an instantaneous velocity. It's going to be an average velocity. If I take this secant line and I scoot T2 closer to T1, so let's say I take this and I'm going to actually now put T2 right here. And I now calculate the slope of this line. That's a little better estimate of instantaneous velocity. And I can scoot it even closer, maybe somewhere right here, and calculate the average rate of change here. And as I scoot this line successively closer, the slope here is going to get closer to the slope of the tangent line, okay? So let me say that again. My secant line is going to get closer and closer to becoming a tangent line, okay? I need for you to know the following. The slope of a tangent line is the instantaneous velocity of the object at t1. And velocity is just one of our many examples. So let's actually look at a Desmos graph of this exact phenomenon. So here I've actually got a simple quadratic function, okay? And let's move this point to, let's go right here, okay? So if we look at this quadratic function, we can see that there is a purple line, and this purple line right here is my tangent line. It is touching my quadratic function at one point. And then I can see this green line, which is my secant line. And as I start to move this green line and I move the green dots closer and closer together, notice that my green line is getting closer and closer to my purple line until here they are pretty close to each other. So I am making the distance between these 2 points get closer and closer to 0. So instantaneous velocity, average velocity. Instantaneous velocity, average velocity, okay? And so we're talking about slopes of these 2 lines, and the closer and closer I can make these two points, the more better approximation I will have of my instantaneous velocity. So that brings us to what we know about slope. An average rate of change with respect of y with respect to x over the interval is the ratio of delta y over delta x. And you guys should go, oh, duh, this is slope as we know it from Algebra 1. Or y of x sub 2 minus y of x sub 1 over x2 minus x1. Or as you lovingly learned in Algebra 1, f of b minus f of a over b minus a. Guys, that's just a difference quotient of slope. This is average rate of change, okay? For the instantaneous rate of change, I need to find the limit of the average rate of change as x2 gets closer and closer to x1. And so we must consider values of x2 on both the left and the right as we take this limit. You'll hear me refer to this expression right here as a difference quotient. A difference quotient. And an instantaneous rate of change is called the derivative. And I know you learned a little bit about derivatives last year in pre-cal, so we're going to call those derivatives. So what in the heck is a derivative? Other than, Miss Lowry, you've just told me it's the instantaneous rate of change. Brings us to this box, the definition of a derivative. Symbolically, a derivative of f of x at a point x equals c, which we'll call f prime of c, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, I want you to think about your limit knowledge that you know so far. We know we can find limits by direct substitution. But guys, if I direct sub here, you can see that's going to give me 0. But why would it be 0? Because guys, we're talking about slope. And slope, I want to make this denominator as small as it can possibly be. I want the difference of the x values to be so small that it's approaching 0, which is why this is approaches 0. So then we think about what slope is, difference of y, right? Change in y. Guys, this is the change in y. y2 minus y1. Well, how do I know that? Because I've picked a point that is so close to my original x value that it's approaching 0. So we're talking about on a graph here. If we think about a graph, I am getting 2 points that are so close to each other that the distance between them is getting close to 0. And this is still slope as we know it. This is still y2 minus y1 over x2 minus x1. But I need for you to memorize this definition. Now, when we say a limit, when this limit exists, if this limit up here exists, we say that f is differentiable at the point x equals c. Now, there is actually another form of the definition of the derivative, and you're responsible for knowing both. The second form says if I want to find f prime of c, it's the limit as x approaches c of f of x minus f of c over x minus c. Now, you're looking at that and you're going, gosh, that's so different. Why is this different? I need for you to know this is still slope. This is still y2 minus y1. This is still x2 minus x1. We're still finding slope, okay? So I want to go into an example, and that's kind of where we'll frame all of our thinking for today. We have a diver who's going to jump from a diving board that is 32 feet above the water. So here is my diver at 32 feet, and this is his function. So I have a parabola opening downward. So I'm just going to make a real quick sketch. He's going to leap up and eventually touch the water, which when we say water, I'm talking about water right here, okay? Now there is another part of this parabola right here, which we're not seeing, but we don't have negative time. So we've got time here, and I want to be able to get some points. So we know we have 0, 32, okay? If I take this function and I could plug into it, let's say at 1, if I plug in 1, we also get 32. All right. If I plug in 2, you should actually get 0. So my picture's not super great. Let's make this picture a little bit better. So here is 2 at 0. I could plug in a half and I get 36. So right here, this is the point 1/2 and 36. And I could also plug in 1.5 and get 20, just to kind of have an idea of what's happening here to construct my graph. So basically he leaps up, he's going to kind of pike and come back down and hit the water, okay? So 1B says, I want to find the average velocity at which the diver is moving on this interval. Don't overthink this. We literally want to find S of 1.5 minus S of 1 over 1.5 minus 1. So essentially, graphically, what we are doing here is S of 1, here is S of 1.5. I am finding the average rate of change, the slope of this secant line in between those 2 points. So that's why we have these values that we've already plugged in. S of 1.5 is 20. S of 1 is 32. This is a time period of a half a second. I get negative 12 over 1/2, or negative 24, and we're going to include a unit. The top is feet, the bottom is seconds. So now what I'm going to ask you to do is you're going to do the same thing here. You're going to fill this in. We're going to do the same thing with 0.9 and 1. So for example, you're going to find S of 1 minus S of 0.9 over 1 minus 0.9. You're going to get that value, and you're going to plug that in right there. And then you're going to do the same thing for this second one here. So you're going to go with these two guys, S of 1 minus S of 0.99 over 1 minus 0.99. You'll get that value, and you'll plug it in right here. And then you're going to do the same thing right here. You're going to go S of 1 minus S of 0.999 over 1 minus 0.999 and get that value, and that's going to go right here. So guys, what I'm asking you to do here is, if you haven't noticed, I am making these intervals progressively smaller, and we're getting close to an X value of 1. So we can see that 1 falls right here. And then I'm asking you to do the same thing on this other side over here and get those values. So you're going to find 6 average rates of change, 6 of them. I will hint to you, you're going to want to use your calculator here. You may even want to use the ask feature. So this is your function that we're plugging into right here. Okay, and so you're going to go and plug in and find 6 average rates of change. So you should have values 1, 2, 3, 4, 5, 6. Keeping in mind that x equals 1 is right here. Now, why do I care about this? I should be able to look at these values in my table and find an estimate for the instantaneous rate of change at 1. If I was able to freeze time right here and find his rate of change, his speed at that moment, I should be able to look at my table and do this, okay? So that's where I'm going to pause, and when you come back in Edpuzzle, you're going to enter in your estimate for the instantaneous velocity in Edpuzzle, okay? And we'll pick up there next class.